family. All right, so how many children are in your family? I don't even know how many people we actually have here today. Somebody else, like, count this. Count how many people. So I'm not wrong.
You're not getting in that sort of breath.
I'm 18. I'm an adult.
I'm still right though.
Why not? Okay, guys. Maybe I counted you. Right. I was like, that's why. Wait a minute. Yep. Yes. Okay, so out of the 28 people that we have, okay, so all of these are going to be out of 28 because we got 28 people in our class. Who are we missing today? I never helpful with that. Do y'all even know y'all's classmates?
No.
Shameful. Not at least 4 people. I know my people and myself. Yeah. We will do one later. Okay, so raise your hand if you have one child in your family. It's including yourself. This is stepbrothers, stepsisters, half brothers, half sisters. How many children are in your family? Okay. What? Sorry. Oh. Oh, okay. Anyone who is under the age of 18. If you are in school, not college, if you are in school, you are a child. Yeah. Okay, sorry. Sorry.
No.
Okay. So, one child. 1, 2, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, you do count yourself. So 9. Okay. How many of you have 2 children in your family? Okay, 1, 2, 3, 4, 5, 6, 7, 8. Oh, this is not gonna work out. All right. 3. 1, 2, 3, 4, 5, 6, 7. Okay, I do want to point out that that's already like majority of our class. Okay. Okay. All right, so where do I need to move you from? Okay, so back down here, we got 9 and we got 6. Starting off strong. How many of you have 4 or more? I'm sorry, 4? Just 4. 1? All right, how many 5? Anybody 6? Anybody 7? Oh my God. Anybody? Okay. All right. Make sure that math is right. And 16.
No, 26.
So we got 9 plus 9 plus 6 plus 1 plus 1. So that's 26. 2 people didn't do what they were supposed to do.
I'm 18.
You have 18 people?
No, I'm 18.
So you have no children in your family?
No, my brother's 20.
Okay. So let's put 1 for you. Let's do 1 for you. Yep. Who's my other person who didn't say it? How many people do you have? How many children do you have in your family? 4.
I'm still in school.
It's okay. We're just gonna throw that in there. All right, go ahead and write this down. So we've got 10, 9, 6, 2, 0, 0, 1, 0. Here it is again. 10, 9, 6, 2, 0, 0, 1, 0. Okay. Is 5.7167 a possible value for x? Look at what x is. What does x represent? Okay, so is it possible? No. Why not? You can't have half of a child, right? Like it's a really touchy subject, yo. Okay. So X represents a discrete random variable. Okay. The word discrete means whole number, right? We're not going to have decimals. Okay. Okay. Calculate and interpret. X is greater than or equal to 3. So the probability of X is greater than or equal to 3. So how many people do we have that were 3? And then there were 2, and then there was a 1 right here. So we're going to have 9 out of 28. Somebody type that into their calculator. 9 divided by 28. Say it again. 0.321. All right, now let's talk about how to interpret this. Okay, so how you interpret this is you say the probability that a randomly selected student has 3 or more children in their fam is 9 out of 28, or you could say 0.321. Question?
Wait, hold on, you said including yourself?
Yes, you messed this up, David.
So then I'll be 8. We'll be 8 and 6.
It's okay. You're the outlier anyways. It's okay. Not the freak. I mean, if we like exclude the fact that all of the people in my family are like grown up, then we have like 14. Like, so I feel you. I mean, if we include everybody. Then-
Especially good.
Okay, so we're going to make a histogram of the probability distribution. Okay, so we're going to make a histogram of the probability distribution. Okay, so come down here. Okay, notice how the x-axis has the number of kids. Y-axis is going to have the probability. Okay, so probably best way to do this is to say like 1 out of 28, 2 out of 28, 3 out of 28, 4 out of 28, 5 out of 28, 6 out of 28. Okay, I should probably make these smaller. We had some weird numbers. David messed up our thing. Okay, so looking at our numbers, I don't have them anymore, so help me. What's our lowest number that we have out of the 28? We had 1 out of 28, right? What's our highest? 10?
Yeah.
There's one group that had 10? Okay, cool. So how do we break this up to make that happen? There's 1, 2, 3, 4, 5, 6. So we're going to go up by 2s. Okay. So 2 out of 28, 4 out of 28, 6 out of 28, 8 out of 28, 10 out of 28, 12 out of 28. I hate histogram. Okay. I know. All right. So how many people had 1 child in their family? 10. Okay. So we're going to go up here. We're going to draw a little line. And we're going to come down here. All right. Remember, with histograms, there's no gaps in between your bars. They're all like smushed together. Okay. All right. How many had 2? Okay. So we'll come in here, draw a line, come down. What about 3? Okay. About 4?
2.
A janky histogram. All right. How about 5? All right. What about 6? What about 7? Just David. Okay. And any 8 plus? Nope. Describe the shape of the distribution. Skewed right. Why? How do we know? The tail tells the tale. And David's chilling over here, right? Okay, and we got like the big arch and then it kind of like tapers off, right? Okay, sorry, David. Should take a picture of the data. Make the next part easier. Okay, the average of the X values is 4.5 children. Okay, so that means that if we add up 1, 2, 3, 4, 5, 6, 7, 8 children, and then divide it by how many groups we have, which is 8, that would give us 4.5 children. It says this value give the average number of children in the families of the students in this class. What is the average? Probably like 2. Okay, well, the answer is no. Okay. But what would be that value? What would be the average? Okay, I'll give you a second to find it. Okay, David said 2.18. Do you agree? Nobody else tested it? No? Okay. You got 2.17. Okay. Yeah. Yeah. Okay. So let's kind of think through this. All right, how many kids we had for 2 children? We had 9 out of 28, right? For 3 children, we had 6 out of 28. I'm getting there. I'm coming back to it. Okay. And then 4 children, we had 2 out of 28. And then 5 children, we had 0 out of 28. 6 children, we had 0 out of 28. Out of 28. For 7 children, we had 1 out of 28. And for 8 children, we had 0 out of 28. How many do we have for 1? 10. Yes, because we're going to talk about that in just a second. So this is what we call the expected value. Plus. Expected value. Okay. Where I'm going to throw some Greek notation at you. Mu of x is equal to sigma. Oh my God. X sub I times the probability of x sub I. So basically what this is saying is for each x value, you are going to multiply it times the probability, and then you're adding all of those up. So if you take this and you add it all up, what are you going to get? So this is accounting for all of your different like number of children. Okay, so take a moment. I want you to add these up. So use your calculator, add it all up. So 1 times 10 divided by 28, etc. Is it 2.17? Is that what you did? That's what you got? Okay, so mu sub x for this class is going to be 2.17. Is that what you did? Is that what you did? Okay, cool. Just checking. Yeah. Because this is the x. This is like the variable that we're talking about. Okay. In this instance, no, because we're talking about discrete random variables. You're gonna have a number. The continuous random variable is what we're gonna talk about in the next lesson. Yeah. Okay. So as a class, we need to calculate the mean and the standard deviation and interpret each. How do we find standard deviation? Do we remember? Uh-oh. Using the calculator. Yes. Okay. So you can do it in Desmos. You can do it in Desmos. Okay. You put in your list and you can do STDEV. Do you remember this? Okay. Go ahead and take a moment, find your standard deviation. You have option 4, add list and spreadsheet, name your data at the top, enter the values. Okay. And so I'll just ask me, like, how do you put it in? You're gonna put in 10 ones, and then you're gonna put in 9 twos. Not across, it should be down.
Okay.
Yep. All right, need you to try it. There we go. You should have gotten like 1.33. Yes. Did you get 1.33 or did you get 1.31? It's the sigma sub x. Your sun silence is very reassuring. So it says sigma and then sub x. It's like an O with a little fancy tail. 1.31. Okay, so if you're going to do this on Desmos, you're going to do STDEVP. I'm talking about sample versus population. This is our population of people that we're trying to look at. Yep. Yep. Somebody get their bread. On your paper, okay, so we got, as a class, we got sigma sub x is 1.31, and we've got the mu sub x, that's the mean of your x, okay, and that was 2.17. Okay, so now we're going to interpret it. Okay, so for mean, it is the average number of children in a family after the long run of randomly choosing many students from this class is 2.17. Okay, so the keywords on this one, is obviously saying the average number. Okay, you need to make sure that you say many students. Okay, so like if we simulated this over and over and over again, that's what's going to happen. You want to talk about it in the long run. And then you want to make sure that you include the number. Okay, so whatever you find for mu. Yes. Yep, I got you. The average number of children in family through the long run of randomly choosing many students
You gotta do like 90%.
from this class is 2.17. Yep.
Why are we using one?
Because if you're talking about something in the short run, then you really can't say that is actually accurate.
So
If we ran that simulation over and over and over again in multiple classes, we should get roughly the same result.
There isn't really many students in this class.
You don't need to, this time you can.
You have the same answers, so no one can. Okay. Okay, and also, if the data from this class, how is it being responded to the rest?
We said from this class. We're not going to talk about, we can't talk about next door.
Why is there even repetition if it should be?
We're going to run into situations where you would have to simulate this over and over again, and it wouldn't be just these people. If we go and do this in that class, we're going to get a different result. But if we run it in this class all over again, okay, it's going to give you the same result. Because in other situations, you might get something different. Hey, how many basketball goals did you make? That might vary from simulation to simulation. Does that make sense? Just bear with me. We're not even done yet. We're not done yet. We're not there. We're not yet. All right. Now, for standard deviation, oftentimes they're going to ask you to interpret standard deviation. I'm going to put it up here so that you can actually see it in the back. That's the number of children in a family. Typically varies by about 1.31 children from the mean of 2.17. So basically, if your family only has one child, probably the person next to you either has one child or they have two children, roughly, right? It's not super far off. Many. What we just talked about. Okay, so we talked about probability distribution. This is horrific. We talked about probability distribution. Okay, we use a little table to kind of show our thoughts. We had the variable, and then we had the probability of the variable. This row added to equal 1, add up to 1. Okay. We talked about a discrete random variable. And it's talking about taking a countable number of values with gaps. All right, I'm gonna read it again. So probability distribution, we use a little table. The probability added up to equal 1. We talked about discrete random variable, which is a countable number of values with gaps. we talked about center, where we talked about the mean, and that's going to be represented by mu sub x is equal to sigma x sub I times the probability of x sub I. This is what we call the expected value. And it's just talking about versus a sample versus a population.
So it's still.
It's still the mean. It's still what you normally know. Yes. Yes. So you've got mu sub x. That's your expected value. Mu is like a fancy m. That equals sigma, which is the sum of x sub I each iteration of x.
Oh,
Mhm.
wait, what is,
Times the probability of x sub I.
what is iteration?
So we had one child, right? That's the first x. So that's one. We had two children. So that's two. So it's talking about the different variables that you can have. We had 1 to 8 kids, right? Right. We also talked about variability, and that was standard deviation. Here is your formula for standard deviation. Sigma sub x is equal to the square root of the sum of x sub I minus mu sub x squared times the probability of x sub I. That formula should be on here somewhere. Yep, what's your question? It is. Okay, we're good. Formula is on here. We're good. So again, sigma sub x is equal to the square root of the sum, parentheses, x sub I minus mu sub x squared times the probability of x sub I.
So what's reset?
That's your mean.
Okay.
You've got to find your mean before you can do variability.
Okay. What is that? Oh,
Sigma.
I thought sigma was for
So in Greek, you've got a lowercase and uppercase. This is uppercase sigma. This is lowercase sigma. Yeah. No. Yes. Yes. Okay. All right. I want you to take a moment. Let's chat. So, Home Alone is a series of American Christmas. Let me try this again. Christmas family comedy films created by John Hughes. There are 5 Home Alone movies. Below is a probability distribution of the number of Home Alone movies watched by a large sample of high school students. Let X represent the number of Home Alone movies watched. So write the event that the student has seen exactly 3 Home Alone movies using probability notation. So really quick, if I wanted to find exactly 3 movies, I'm going to say probability of X equals 3. Okay, now this box is missing. Okay, but we have all the other boxes. This row should add up to equal 1. So we're going to say 1 minus 0.15, 0.42, 0.32, 0.02, 0.01. Which when you do that, you're going to get 0.08. That one's pretty easy, right? Okay. Let that one be the easy one. All right, explain in words what P of X is greater than or equal to greater than or equal to 1 means. What is this probability? So what does that actually mean? The probability that student selected. Why does it crap out like at the very, very end? Selected has seen at least one movie. Okay, so again, probability that student selected has seen at least one movie. And so that's going to be 1 minus 0.15, which is going to give us 0.85. Yep, go ahead. You good?
Yeah.
Okay. Because we went at least one movie would be greater than 0, right? Okay. Yep. You can put that. Yeah. Hey, Jasmine just brought up a good point. The probability that a randomly selected student, randomly student selected, has seen at least one movie. Okay. I feel like as a reader, it's easier if you just use like the lingo, like at least, greater than, that kind of stuff. That makes it easier to grade. So yes, you can use it that way, but sometimes people miss things. Yeah. All right. So we're gonna fill in the histogram and then we're gonna describe its shape. So we're gonna fight. And you know. Okay. So on 3, how much did we have? What was our probability? 0.08, right? And so that's gonna be right in here somewhere. So describe the shape. So we've got skewed right, but we have one peak right here. Okay, so one peak at one movie. Okay, so when you're trying to describe the shape, most of the time, I don't want to say most of the time on these, but let's say that it has a general shape of skewed right, but it's just got some craziness at one specific spot. You can be like, hey, at this one peak, it's a little too high or whatever. Okay. I'm sorry, skewed right. Like I swear, I'm like, yes, I have bad handwriting, but this is really bad because it's not okay. I do. I thought this would be okay, but like it says one peak. This is me trying to write it. Like I'm all right, so one peak at one movie. I promise. This is not as bad. I might just start typing it in. That might be a good idea. David, come right. Yes. All right. So calculate and interpret the expected value. Okay, so when we do this, remember, we're going to take each value and multiply it times the probability. Okay, so we've got 0 times 1.15 plus, yeah, I can write numbers fine. 1 times 0.42, first of all. 2 times 0.32. This is so bad. 3 times 0.08. Less. I think it's only certain parts of the board.
So you can.
I really just need to suck it up and use the iPad instead. I just don't want to have to do all of the backward. Okay, so you're gonna say mu sub x is equal to all that junk. When you add it all up, you're gonna get 1.43. Remember, when we find the average, a decimal is okay. Okay.
Oh, because aren't all of them Greek? Aren't most of them Greek, right? So we got most of them. Okay.
I think it's lower.
You know that.
I used to. I'm gonna look it up. Okay, so what would be the interpretation of this? What would be the interpretation of this? Say it again. The expected value is 1.43. What does that even mean though? Okay. All right. Okay. So to interpret this, also David, this is lowercase, this is uppercase.
Yeah.
You're welcome.
Normal.
Okay. Yep, normal M. It was lame. Okay, the expected value is the average, okay, number of movies. The average number of movies after the long run of choosing many, many students. I hope y'all writing this down. Students is 1.43. So the average number of movies after long run of choosing many, many students is 1.43 movies. So Jasmine, your interpretation of it wasn't bad. You got to include long run, many, many. Okay. All right, now we're going to calculate and interpret the standard deviation of X. Don't show work, which means that you would have to put it in your calculator. Yep.
Like the many
Mm-hmm.
on the when we do the AP exam,
Mm-hmm.
that's like one of those like keywords, right?
That's what they look for. Yep.
Okay.
Yep.
This is like too many.
Too many. Many, many is too many. All right, so we're gonna get sigma equals 0.97. Okay, and that means the number of movies watched by a student typically varies 0.97 movies from mean of 1.43 movies. The number of movies watched by a student typically varies by 0.97 movies from mean of 1.43 movies. Number of movies watched by a student typically varies. Random student. 0.97 movies from mean. 1.43 movies. All right. Just mess up his table. Okay. So how much do you get paid? Suppose you got a new job and each day your boss draws a slip of paper from a bag to determine your wage for the day. First of all, that would be horrible, right? I think so. Okay, let the random variable X equal the daily wage. Okay, so what is your wage for the day? Okay, all right. So I would have y'all add the data to the table, but how many people actually work in this class? Okay, so like half. Okay. So with that being said, we've got $1, $5, $7, $10, $15, and $25. I'm gonna give you data just to make our lives easier. So 3 out of 30, 6 out of 30, 7 out of 30, 10 out of 30, 3 out of 30, and 1 out of 30. Okay, so is X a discrete random variable? Is it a countable number of values with gaps? Are there gaps? Yes. Okay, is it a countable number? Okay, then it is a discrete random variable.
So probably just be,
Yes. So it's a countable number of values with gaps. Okay. What is the probability that a student makes $17 per hour or more? So how many make $17 or more in this scenario? 1 out of 30. Okay. So probability of X being greater than or equal to 17 is 1 out of 30. Okay. Option 2, your boss decides she could also assign wages so that employees would get any amount, even crazy decimals, from 10 to 20, and all amounts are equally likely. Okay. I don't know. Why would you also have your wage drawn from a bag? But here we are. It's fine. All right. So let Y represent the daily wage for this scenario. Is Y a discrete random variable? Is Y a countable number with gaps? No. Okay. Because Y has infinite possible values. Okay. With no gaps. Okay, so now, what is the probability that a student makes $17 per hour or more? So we're going to say probability of Y is greater than or equal to 17. Okay, so think about it like this. Here's your area, right? How many made 17 or more? Say it again. 1. Okay, so right here, we want to know 17 or more. Okay, and you told me that there was only 1, right? And there are how many numbers between here? 17 or more. Okay, so 3. So what does this 1/10 represent? Okay. Okay.
okay.
So your total area is 1, right? Okay, you've got from 10 to 20, right? But we're only focusing on 10 to 20 right here. Yeah, look at our graph. Right. Could you get 0.999?
No.
I mean, monetarily, can we?
Well, how they include the fact that you get to the dust, that's not.
So there was the hundred, I think there's like 17.
So
With like 9, because it was like.
okay. Okay. All right, so the area of this box is 3 by 1/10. So we're trying to find that probability of greater than 17, right?
Like 17 all the way to 17.99, and then we'll simplify that to 1/10.
Okay.
So that can stop probability. So
Okay.
that it still be like the probability of conditions of higher than 3
Okay. So our area is going to be 3 times 110 is gonna give us 0.3. David lost it on that one. We're gonna relate it back to the normal distribution. It'll make sense in just a second. What's up, David? Good. All right. So the probability is going to be 0.3. Okay, now option 3. I'm sorry. What is this option? This is going to be a continuous random variable. I feel like that's easily identifiable, right? It's no gaps, there's decimals, okay? All right, on option 3, wages are assigned randomly from a normal distribution with a mean of 15 and a standard deviation of 3. Okay? So let Z equal the daily wage from this scenario. Is Z a discrete random variable? Wages are assigned randomly from a normal distribution with a mean of 15 and a standard deviation of 3. Is it a discrete random variable? Can you get something that's in between 12 and 13? With this scenario, can you?
It's going up and down by 3. You only get a whole number.
But the third one is the standard deviation. Yeah. It's not like you can still get decimals.
You can get something in between.
It's just that three is just like
Nova was not happy with that answer.
like 2.8.
Discrete has gaps. Discrete has gaps. Continuous does not. Is the normal distribution, does it have gaps?
No.
No. No, no, no. Okay, so this is not a discrete random variable. Z has infinite possible values. Okay, so now on the next one, it says, what is the probability that a student makes $17 per hour or more? Okay, so throw back to like unit, I think it was 2. The way you would find this is you would say the Z-score is 17 minus our average, which is 15, right? They tell us this. And then we're going to divide by our standard deviation, which is 0.3. I'm sorry, is 3. So that's going to equal 0.67. What do we do with our Z-score? You go into the table and you look for 0.67, and that's going to give us an area of 0.2514, which means that the probability of Z being greater than or equal to 17 is 0.2514. For visual people, here is your mu. 17 is like right in here. And we're trying to find greater than. Again, remember this notation. I don't want you to be caught off guard by it. It's your mean, comma, your standard deviation. Normal distribution.
Oh.
You see what we done using our brain? You'll be fine. Okay. Summary, ready? Okay. We talked about discrete, and then we also talked about continuous. Okay, remember, continuous is you have no gaps. It's infinite. Okay, some examples of this are going to be normal distribution and uniform.
Then generally
If it is a whole number with gaps, then it would be discrete. Otherwise, it's continuous. Say again. It's got to be countable numbers. Think about elementary school. Yeah, like first grade. What were the numbers they taught you? All right. So hopefully this will help just a little bit with probabilities, which is what we also talked about. We found the area under the curve. Okay, that is finding the probability. Okay, we talked about the normal distribution. Okay, and we found some section of the normal distribution. Remember, your z-score is x minus mu divided by the standard deviation. We also talked about uniform, and this was that little box area that we all didn't like. Okay, when you do uniform, I'm gonna draw it first and then explain. Oh, B equals 1 over K. So remember how Victoria said, hey, we went from 10 to 20 and we have 10 possible numbers, right? So then we said 1 over 10. That's what was right here. That was the height of the box. Okay. This little space right here is going to be B equals H. That's going to be the length of the box.